Welcome back. Today we are going to talk about a topic which is very closely related to what we have been discussing so far, but there is a little difference. So, in continuation of our discussion on microstates of a system in equilibrium, today we are going to talk about the microstates of a system which is comprised of n non-interacting particles as before, but now we have taken up the problem of using n identical non-interacting particles. So, let us go ahead and see what we can do with these identical non-interacting particles, and therefore, unlike the previous discussion where we had each particle comprising the system to be different and distinguishable from each other, now all the particles that we are going to deal with at the microscopic level are going to be exactly the same, and you cannot tell the difference of one particle from another one. So, now the chemists deal with certain types of systems, and there are certain certain particles that they are always thinking about. So, let us try and have a look at the kind of identical particles that are of interest to practicing chemists. Of course, the first choice that comes to your mind are the electrons. Chemists work with electrons, and this is a cartoon representation of electrons, where I have represented by these spheres the typical electronic cloud, a symmetric typical electronic cloud, probably characteristic of a 1s electron. It may so happen that the system that the chemist is interacting with is comprised not only of electrons, but it is basically comprised of a set of atoms. For example, I can talk about the set of atoms as, okay, this is a typical microscopic picture of a cluster of 3 argon atoms. Now, is there a way where I can say I can distinguish between this atom from this atom, or this atom from this atom? The idea is none of them are distinguishable as far as all the measurement processes that I have available with us. Then, of course, as a chemist, we deal with molecular system. So, this is a typical microscopic snapshot of, say, a nitrogen gas. As you see that each molecule now is comprised of 2 atoms, atom 1 and atom 2. Now, these 2 atoms give me one particular molecule. Now, if I look, let me label this as molecule 1. Now, if I pick up another molecule like this, and if I put a label to it as number 2, is there any difference between number 1 and number 2? The answer is no. Therefore, for all practical purposes, if I go on considering each and every molecule present in a nitrogen gas, I must say that all of them are identical. Therefore, if I am looking at the property of these systems, then I must realize that the microscopic state of this system is going to be characterized by a set of identical particles. And here is another example where I have a much more complicated molecule. So, what I am showing here is, look at this particular molecule. This molecule is comprised of 1, 2, 3, 4, 5. It has 5 atoms, and does not matter which molecule of this system I pick up, I have the same atomic arrangement, and I cannot distinguish between molecule 1 from molecule 2 or between molecule 2 and 3. As a result, I would say that in most of the systems that the chemists deal with, we are dealing with identical particles. Therefore, in continuation to the previous discussion on how do I characterize and count the number of microscopic states for a given thermodynamic condition, today we are going to pick up this problem of counting the number of microscopic states in the identical particles. So, in this case there is a generic description that is found to be extremely useful. Now, as I said that one class of the particles that we are interested in are electrons. Similarly, there are several other quantum particles that we know about that can be broadly categorized into two different classes. One class we call them fermions and the other class we call them bosons. Now, let us see what is the difference between these two classes of quantum particles. The first one, fermions, it is said that if you have a system comprised of fermions, then no single particle states may be occupied by more than one particle. I will explain to you what each of these terms in this definition mean, but at present it seems to imply that if you have a single particle state, then the occupation number of this single particle state can be either 0 or 1. Okay? And fermions are usually characterized by half integer spins. Now, if I look at the contrasting definition of what I have as bosons, then what I find is that here also we will talk about the single particle states, and the difference between the fermions and the bosons is that the single particle state can be occupied by an unrestricted number of bosons. Now, if I look back, in the case of fermions, a single particle state has only two possibilities. Either it is empty, that is occupation number is 0, or it is singly occupied, which means that this particular state has only associated with only one particle. On the other hand, in the case of bosons, as you see that for a given single particle state, you can have a very large number of particles associated with it, so that the occupation number can start from 0, which is an empty single particle state, then singly occupied states, doubly occupied states, and so on and so forth. So, what is the maximum number of occupancy over here? It is understandable that by this definition that the maximum occupancy is going to be infinity. If I have an infinite number of particles associated with the system that I am understanding. I will come back to this distribution of occupation numbers, this concept later on, and how to characterize the microscopic state of the system with it. But for the time being, it will suffice to know that fermions are characterized by two things: single particle states as well as the occupation number and the limited choice for occupation numbers. And the bosons, they are characterized by single particle states where the occupation number can be anything starting from 0 to infinity. Now, let us go back and now try and check what are the examples. A typical example of a fermion is an electron. On the other hand, a typical example for a boson is a photon or a phonon. So, let us now take up one by one what I mean by the single particle state and why, for example, electrons work as fermions. So, if I want to derive the single particle state of an electron, it means that I shall be solving the Schrodinger equation at the microscopic level, that is the equation that we solve to obtain the quantum mechanically allowed states of the system. Now, I have said a single particle state, which means that for an electron I will solve the electronic Schrodinger equation when only one electron is present in the system. So, can you tell me which system gives me this an example of just one electron present, where I can solve the electronic Schrodinger equation analytically? I am sure you have learned in your quantum mechanics or quantum chemistry class that the Schrodinger equation of a hydrogen atom can be solved analytically, and these are the allowed solutions that we have known. So, first we have the lowest lying eigenstate, which we call as the s orbital. Okay. So, this is a single particle state of the electron, where we have plotted the this is a three-dimensional plot for the probability of finding an electron around the nucleus of the atom with say 95% probability. This is called an isosurface. So, basically I am connecting all the regions around the nucleus where the probability of finding the electron is 90 for at least 90%. And so, for the s electron, what I find is that this is a small spherical region, and there is one thing that you note, that this has been colored using a single color. So, this is a single particle state of the electron in a hydrogen atom, and this is the simplest representation of a single particle state of an electron that we know of from our study of hydrogen atoms. There of course are other known possible single particle states, but the difference between S and P etc. is that if I am talking about only the lowest energy state, it has to be 1s, okay? And then you will have to go for higher energy states associated with n equal to 2, and then you can have 2s and 3 p's. And as you can see that when you have the p orbitals, I am using two different colors. Why is that so? That is because the solution of the Schrodinger equation is the solution to a wave equation, and therefore, the solution of the wave equation actually has a phase factor, which says that the wave function is positive in some regions of the solution and negative in some other regions. Okay. Now, since I am plotting the probability, I am actually looking at the square of this wave function, and that is dressed with some other factors. Now, the moment you square it, then you have lost where the wave function was showing a positive sign and where it was showing a negative sign. Now, this has actually a lot of importance as far as this overlap of these orbitals are concerned, and therefore, it is found extremely useful if you use two color codes. For example, here in this case, this part of the single particle state, that is the px orbital, originally had the say the positive sign underlying associated with the wave function, and this portion had a negative sign. Okay? And therefore, these two are colored differently, although each of them signify the probability of finding the electron in this area, either here or here, with typically 90 to 95% probability. Now, the basic point here is not our concern about what these things mean, but the candidature of the solution of Schrodinger equation to give us single particle states of an electron. So, if I assume that the single particle state of an electron is given by these hydrogenic atomic orbitals, then I can start by thinking of attaching one electron to one of these states. Now, then the microscopic state of the electron will be having two parts. One is the orbital part to tell us whether it is present in an s orbital or a p orbital or even in a d orbital. So, let for this time being concentrate on placing one electron in an s orbital. Okay. Then the orbital part of the electronic wave function is given by the 1s orbital. Now, this electron, in addition to its orbital properties, will also have another property, which is spin. Now, this spin may be an up spin or down spin, but we do not know simply because we have not applied any external field. It is only in the presence of an external field that the difference between the two spins will become apparent, and therefore, the single particle state of this electron that I am talking about, this is given by 1s. This is the orbital part and this is the spin part. So, this is one possibility. The other possibility is the same orbital part, but the spin part is different. That is, it has a so called down spin. Now, in the absence of a field, these two are two different two possible single particle states. Now, what happens if I bring in another electron? Okay? And the second electron is also capable of occupying any of these single particle states. The second electron also has in its wave function an orbital part and a spin part. Now, the question is, when the two electrons are together in my system is comprised of two electrons. In that case, the question is it possible to have both the electrons having, say, the 1s orbital wave function and both up spins? So, the question that we are posing here is as follows. I now have two electrons. When I have two electrons, then I am assuming that both of them are occupying the 1s orbital. So, now there is one part of their single particle state missing, and that is their spin part. Now, we are asking this question, is it possible that electron 1 is going to have a single particle state like this, and at the same time in my system there is the second electron which is going to have a single particle state like this? So, this is my option 1 for the 2 electron system, option 1. The other option obviously is what I have drawn on the top. So, the first electron and the second electron, both of them have as the orbital wave function the 1s electron 1s orbital, but one of them is having an up spin and the other one is having a down spin. So, let us say that this is my option 2. Now, from our knowledge of atomic structure, we know that this option is not valid, but this is a valid option as put forward by the Pauli exclusion principle. And therefore, we would say that using the Pauli exclusion principle, the single particle state for 2 electrons are going to be like this, that the orbital parts can be the same, but their spin parts are going to be different. And that is why we always write the electronic configuration of a system where there are 2 electrons like this, which means that I have hydrogenic 1s orbitals. The first electron is occupying the hydrogenic orbital with, let us say, an up spin, and the second one, if it is having the same hydrogenic orbital 1s, it is going to have a down spin wave function. Now that we have talked about the microscopic states of an electron, the possible microscopic states in terms of the single particle states, let us now move over and talk about the wave particle duality. But maybe before that, let me go back and once again emphasize the fact. In summary of this slide, we can say that an electron is a fermion because it has two single particle states accessible to it for a given single electron. One is 1s upspin, the other one is 1s downspin, and therefore, one electron can either occupy one of them or not. So, these are ideal cases of the fermions. Now, let us look at what happens in the case of photons. We know that light, when it shines on any media, any surface or any matter, we generally understand light as an electromagnetic radiation which is associated with wave nature. So, it came as a big surprise almost 100 years back that the particle nature of light was proposed, and the quantum model of light then said that light comes in discrete packets of energy and not in a continuous fashion, and these discrete packets of energies are called photons. Okay? And do you know the kind of evidence that was put forward in support of this theory? Yes, Crompton effect, photoelectric effect, these are the different experiments which came in the beginning of the 20th century, for which Einstein developed his theory of the quantum nature of light, and this photon was proposed to be a package of energy having no mass. Okay. So, how do you define the microscopic state of a photon? You say that if you have a light of certain wavelength lambda, then you can associate with it a frequency nu. This is a frequency nu which will tell you about the energy of the single photon, and the single photon energy is then given by h nu, where h is the Planck constant, and you can replace nu by c by lambda, therefore relating the energy of the single photon to the wavelength of the light. So, if I look at the visible light, it is very easy to show that the wavelength associated with the photon is about 10 to the power minus 6 meter. Now, as a result of having this wave particle duality, you must appreciate that I am having a stream of discrete packets of energy impinging on whatever matter I am looking at, and this impinging train of packets, they also behave like waves. That is because if you allow the light to go through some kind of slit, as you may have performed some slit experiments, you see that there are certain diffraction patterns formed which are typical of the wave behavior, and simply because any number of waves can be superimposed to give you either constructive or destructive interference, you see that light passing through this aperture gives you an intensity, the diffraction pattern which has varying intensity, as has been recorded in this picture. Therefore, the conclusion from here is, yes, the microscopic state is of light is comprised of quantum units called photons, which have definite energy values, which do not have any mass. And if I want to think of the number of photons that I can associate it in a given single particle state, there is no restriction, and therefore, I would say that a photon is a boson by definition. Similarly, one can think of the lattice vibrations in a solid as bosons. Now, I will just introduce the name phonons here by saying that when you have a solid, this is a simple one dimensional representation of a periodic solid. These are the different lattice points that we can see here, and there are atoms at rest. But in real world, you do not have the atoms at rest, but they are capable of executing small vibrational motion about their mean position at the lattice points, and this would generate some kind of displacement along this direction, along which we are periodically seeing the placement of the atoms. So, these are known as the longitudinal vibrations. But it may so happen that if you have a 2D lattice, a two-dimensional lattice, there may be displacements in the directions perpendicular to the longitudinal direction of longitudinal vibration, and these vibrations are called transverse vibrations. Now, it has been proposed that these vibrational modes that are generated by coupled vibrations of the different atoms in these lattices, these are quantized, and these quantized modes of vibration of a solid is known as a phonon. Now, if you look at the energy of phonon mode, then it is once again given by the Planck's constant multiplied by the frequency of the phonon mode. Okay? And in this case, you can relate it to the wavelength of the phonon, because these vibrational motions, as has been shown here, generates a wave like nature of the vibration that propagates through the medium, and therefore, here you can talk about the wavelength of vibration as well as the velocity of the phonon that determines what the energy of the phonon is. The other thing that I would like you to note is that the wavelength of a phonon is 10 to the power minus 10 meter. What was the wavelength of a photon? It was 10 to the power minus 6 meter, and therefore, although both photon and phonons are bosons, they have very, very different the energies that when we consider them in detail. So, in both the cases of phonons and bosons, what we find is they are it is possible to accommodate them in the same single particle state. So, the next question that we will ask is, can we now count the number of microscopic states possible for these identical particles? This is what we will see next.